Okay. Okay, thank you guys. I hope you are not tired to hear so many, let's say, fancy topics. Yeah, I'm the last one. My name is Zhipeng Wang. I'm a research associate or postdoc at Imperial College London. And I'm also work as a blockchain research lead at Flock. So today I'm very honored to talk about our, let's say, research results on Flock, and we also have its implementation in practice. So the title is Defending Against Poisoning Attacks in Federated Learning with Blockchain. And this research is co-authored with our colleagues from Flock and also the colleagues from Imperial and also Shanghai Artificial Lab and also CMU and also from the University of sorry, I don't know how to pronounce this name. But anyway, this paper is got accepted at IEEE Transactions Artificial Intelligence. So before we dive into the concrete construction of Flock, sorry, how can I, oh yeah, it works. I would like to present more background about DAI or decentralized AI. This was an ongoing, let's say, research topic that is granted by some academic grant that we are currently working on this topic. I would like to first present a general introduction of the landscape of decentralized AI. Since today we have already heard a lot of interesting topics on this direction. So in our research, we would like to answer several questions, but they are the two most important ones, I think. So we would like to answer what is the general framework of existing DAI protocols, and how can blockchain help an AI protocol to be more decentralized? We have already heard that blockchain can be used to build the incentive mechanism, and it can also be used to construct the access control. So we propose this framework. To maybe it's not that precise, but in general, it's like this. When we talk about model, especially AI model or decentralized AI model, so at the beginning, there should be a task creation, which means when someone would like to achieve a model, they will first define what kind of model task they want, and then to finish this model, we need to do some data preparation, some public data or private data or unique data. And then we would like to perform the training. Of course, we need some computation resources. That's why well, some people will buy some GPU or use their own GPU or CPU to train the model. And finally, after all those things are ready, they can start the training, and the training can be decentralized. And once we have the trained model or generated model, this model can be used to do some inference. And the inference, the model host to perform the inference, let's say to support the inference can still need some computer resource. And in this way, we will also consider the model marketplace, which means when there are a lot of models, how can we choose the best one, or how can we let users to choose the one they want? And finally, it's the application. For example, can be used for IoT and also can be used for some DeFi exchanges or other traditional machine learning applications. So the second question is that what are the functionality of blockchains for DAI? So I think at least from the existing protocols, DAI protocols, we can say that blockchain can serve at least for incentive mechanism, which means we can ask people to pay the fees if they want to use the model, and we can also reward the participants if they contribute their, let's say, their model or their computer resource. And the blockchain can also be used to be the public reference, which means people can refer to which model is the best if they have, let's say, they have a voting mechanism to determine which model is the best. And there was other functionalities. So based on those framework and this, let's say, the matrix we served. Sorry, this is just a part of the table we made. And you can see that some of them are still ongoing because we need more confirmation to analyze the detailed things. So, but we can see that in total we analyzed more than 50 protocols. We can see that from this table, we can see that many of the protocols, DAI protocols, they focus on one or two, let's say, steps in the DAI from life cycle. And the blockchains are indeed very important for these protocols. And we can see that many of them, they are also asking their participants to stake, which means they also got the inspiration from POS or something like that to enable the security. And that's the key takeaways of the existing DEI protocols. We can see most of them, the 2 points I have just mentioned. And the another point is that we still don't know, although we are talking about decentralized AI, but we don't know if they are still, if they have already achieved full decentralization. Because even in nowadays blockchain for Bitcoin and Ethereum, many people are still argue that maybe to some, I don't know, at some points, we are not that fully decentralized. So I think for we have the same issue for DAI projects, because different from the pure blockchain protocols, let's say, or something like DeFi protocols. When we are using we are building DAI projects, we have to rely on some let's say centralized components. So such kind of components will cause the DAI projects are not that, let's say, decentralized, but we are still missing maybe some more precise quantification results on this part. So that's what I would like to give some general background of DAI. And now I would like to dive into more in Flock. You can see that's what we have done here. So that's the general framework of Flock. Although the name or the title of Flock is from Federated Learning on Blockchain, but now Flock is not just about blockchain, just about federated learning. So federated learning is one part of Flock, but it's also the unique part of Flock. And we also have this AI arena in which way we have this decentralized training and decentralized validation. And we also enable participants to create their task. And the participants will, for example, training nodes and also validators, they will leverage the public data to train the model. And we can achieve the consensus model in this AI arena part. But if we want to further fine-tune the trained model, we can go to the FL Alliance part, which is the federated learning part, because here the participants, they will contribute the unique data to further improve the model. And finally, the model can also be used in the AI marketplace. So today I will focus on the federated learning part, which is also the paper I showed at the beginning. So some brief background about federated learning. So in federated learning, there will be two types of participants: clients and also aggregator, or what we call the centralized server. So the client, they will train the model using their own data, and then they will transfer the trained model to the aggregator, and the aggregator will aggregate the local models from the clients and then generate the global model. And there will be several rounds for federated learning, which means after one round is finished, one client they can download the aggregated model in the previous round and continue to train that model. So and finally, they can achieve the model they want. There are many applications of federated learning. For example, in hospitals, each hospital, they have their own data for their patients, and they can cooperate with other hospitals to train some model to help them to fix some, I don't know, some issues, some issues. And in this way, they can perform in such kind of model. But there are some issues in traditional federated learning. That's what we call the poisoning attack. Imagine that there is a malicious client who was a participant into the game, But this malicious client, they just let's say they just contributed random numbers rather than train the model honestly. So in this way, this malicious client can put some poison data into the trained model. So finally, the model cannot be let's say as good as the honest participants want. So there are several traditionally there are several existing solutions to mitigate such kind of attacks. So one existing solution is that by using some proof of correct let's say computation or zero knowledge proofs for that. So in this way, although we can achieve the things we want if we use zero knowledge proofs. For example, when a client they perform the training, they also generate a proof to show that they have actually performed the training. But the question is that there are at least two let's say two issues for this such kind of solution. The first one is that it's hard to define what is a correct training, especially for a client, for one single client, by using their own unique data. And since zero knowledge proofs, although nowadays such kind of techniques has already been deployed a lot, they are still they still require a lot of additional, let's say, computation costs for client. So in our solution, we are inspired by POS mechanism of Ethereum. So in which we would like to leverage the incentive mechanism to reward the good behaviors of FL participants and to slash the clients who perform maliciously. So as we said, we got the inspiration from POS. So as we said, as we know that on Ethereum, when a validator or a block proposer, if they did something wrong, they might be slashed. So based on this, we proposed the solution for federated learning, for blockchain-based federated learning. So we require that the participants or the clients, now we call them the proposers, they have to stake and to participate into the game. And in each round, the voters and also the proposers, they will be randomly selected. And the proposers, they will perform as the traditional federated learning clients do. They will train the model, and then they will upload the model to the upload their local model updates, and the aggregator will perform the model aggregation, and then the voters, they will vote, they will download the model, and then they will run, they will evaluate the aggregated model based on their own data. And then if they think that the model is good, then we will vote positively. Otherwise, they will vote negatively. And when we will consider the aggregated voting results. So if this aggregated voting results is negative, then the proposers in this round will be slashed. And also for voters, we will also reward them if their voting results are the same as the aggregated voting results. Otherwise, they will also be slashed. So that's a very let's say straightforward solution, and also very simple solution. But our experiments show that such kind of solution can indeed work to mitigate the malicious behaviors. So that's our detailed, let's say, diagram. Sorry, here we show the miners, but actually in practice it can be the Ethereum block proposers. Because when we drew this diagram, Ethereum has not been merged, so we call them miners, but actually it's Ethereum proposers. So you can see that for each round we might have two situations. One situation is that when we select the voters and the proposers, if all of them are honest, then in this way all of them will be rewarded. And otherwise, if there are some malicious proposers or malicious voters, and the voting results might identify them, and then all of them will be slashed. Although some of them will not be identified, because let's say the effect of the malicious proposers is not that big to downgrade to degrade the final aggregated model, but we will run it multiple times. So we have proved that in the let's say in expectation the final reward, the final stake of malicious clients will be lower than a threshold or predefined, and which means they will be slashed out. So yeah, that's our detailed algorithm. This is what we just said. For each round, we will check the aggregated voting results, and to determine if the proposers will be slashed or not. And we will also check the difference between the voting result of each voter with the aggregated voting results to determine if a voter will be slashed or will be rewarded. And we have done the experiments. We just do a very simple standard binary classification task, and we used a small data set, which is the Kango Lundy Club data set 4, and we set 50 clients, and initially they will stake, let's say, 64 tokens, and this is our configuration of the machines. And we also consider for each round we define the 10% of the clients will be randomly selected as the proposer, and the remaining ones will be the voters. And we performed experiments for when the, let's say, the malicious ratio of clients the ratio of malicious clients is from 10% to 40%. And this is our experimental results. At first, we just consider the case of the malicious voters. And we assume that if, we can say that by using this case, by using this, the design, the malicious clients, if a voter is malicious, then the expected tokens of this voter will be decreased to 0. So we assume that all rational voters will be honest. So based on this assumption, we also perform we also analyze the token distribution of proposers. So we can say that when we set the slash token for each round is 8, which means 12%, about 12% of the initial stake tokens. We can see that for the honest proposers, their token, the average token will increase, and for the malicious ones, their tokens will decrease. And we also considered when we use different slash amount, we can see that for the largest slash amount, of course, the malicious clients, the tokens of malicious clients will be decreased faster than that case when we use a small amount of slashing token. So we also consider the case for the honest proposers. So it's let's see, for the honest proposers, their tokens will be increased because they got the slashed tokens from malicious proposers. We also consider the survive time, which means after how many rounds the malicious proposers will be kicked out from the system. We say that we can see that if the slashing amount is larger, then the quicker the malicious proposers will be kicked out from the system. But we also find that if we have a very large slashing amount, then we cannot avoid the case that some of the honest proposers they will also be slashed because as we said at the beginning, for each round we will consider the total, let's say, the aggregated voting results. So the aggregator voting results will determine that for this round, if all the selected proposals will be slashed or not. So which means in the case that in the round that there are some malicious proposals, then the selected honest proposals will also be slashed. So we have to be very careful about, let's say, choosing the correct slashing amount. And that's the case we have already showed our results with the case with the federated learning with average aggregation without malicious clients, and also the case with malicious clients. So that's our design is the red lines. We can see that we can achieve almost the same performance with the blue line, which is the case that there is no malicious without any malicious clients. And finally, this is another thing to prove to show it's very important to choose the let's say the slashing amount. Because you can say if we have a very large slashing amount, then the results will not converge that fast as we want. Yeah, so that's the conclusion of the federated learning design in Flock. So as we said, we leverage the staking algorithm, and we also proposed the slash and reward mechanism to mitigate the poisoning attack. And the actual algorithm is implemented in Flock. And besides this, we also proposed the solution to mitigate the case of malicious aggregator. Because what we just said is about the malicious client. But in practice, the aggregator can also perform, let's say, maliciously. So we propose that in this case, we leverage zero-knowledge proof to let's say, ask the aggregator to also generate a proof to show that the aggregator actually has aggregated the local model updates from clients. So in this case, we can also leverage blockchain as references. So there should be a hash value, hash function for the encrypted, let's say, aggregated results. So yeah, so that's all of what we have done so far for Flock. We have proposed the incentive mechanism to mitigate the malicious behaviors from the client side, and we also proposed a zero-knowledge proof-based aggregation algorithm to mitigate the malicious behaviors from the centralized aggregator side. So, and now we are also investigating to build more, let's say, to build a protocol beyond the federated learning. And yeah, if you are interested, you can refer to our papers. Yeah, I think that's all for my presentation. Thank you.